Hello and welcome to our webinar, AI in Healthcare Hyperhelp. My name is Christos Chatzichristof. I'm a postdoc researcher in University of Leuven in a group of studies in the electrical engineering department, and I'm also affiliated as an academic expert with VAIA, the Flemish AI Academy, which role is the lifelong learning for AI in general. So in this webinar, we will try to see how AI has influenced healthcare and what would be probably the future. So I will try to first introduce some general concepts about AI. So AI refers to the ability of the machines to perform tasks that usually human-like intelligence was needed. During those tasks, machines usually learn. So although AI became really famous in the news the last months or year, it's already part of our lives for more than a decade. If you have been using smartphones to take pictures, if you have been browsing to the internet in search engines, if you have been using cars with some smart auto driving, you are using actually AI. And let us see more in detail the timeline. So in 1950, Alan Turing developed the Turing test. The Turing test was the first test trying to see whether a machine can mock people that is human. So someone interrogates a machine, asks questions, and if the machine persuades the interrogator that it's a human, then it passes the Turing test. The Turing test is considered very difficult for machines, and the first chatbot that managed to pass it was in 2014. 1956, John McCarthy established the term AI, and in late 60s, we had the first chatbot already in healthcare, which is called Elisa. So Elisa is a chatbot for psychotherapy. As you can see, it might not be as fancy as ChatGPT looks like, neither so smart if you read the text, but it's already the first attempt to introduce AI chatbots in healthcare. Elisa can be seen in the Museum of Technology in Berlin. And then in beginning of 1970, we had the first consultation systems and therapeutic advisors for the doctors to help them with decisions for their patients. From 1975 till 1989, we had what is called AI winter. Due to lack of computational power, due to lack of new technological advancements, we didn't have a lot of AI applications going on until early 1990, 1989, where we had the backpropagation algorithm, and we had some improvement in GPUs and computational power, which allowed the evolution of deep learning area in the beginning of our century. And the last years, from 2017, we have already the first FDA approval for applications with AI in healthcare, so cardiac measurements, retinopathy. So AI is already part of the clinical routine for some of our hospitals for more than 5 to 6 years. Let us see some basic categorization of AI algorithms that will be necessary for the next steps of this webinar. So usually AI algorithms are separated to supervised and unsupervised. In the unsupervised case, we have a bunch of unknown data, in this case brain signals, and the model tries to separate them, to classify them in a predefined number of different classes, groups. Usually, in order to achieve an unsupervised classification, you need a lot of data. In this case, we see that the model classifies the signals in 3 different clusters. In the supervised case, we have known data. In this case, we have brain signals that belong to the green, blue, or orange cluster, and then an unknown data point arrives, and the model needs to assign to one of the classes. Here, you can see that it detects that it belongs to the orange class. And then a further classification of machine learning models is the handcrafted features-based models versus deep learning. So in the first example, where you see an MS, a multiple sclerosis use case, we have as an input an MRI, then the engineer or the data science needs to extract some features from this MRI based on prior knowledge by clinicians. So in this case, it can be the gray matter volume, it can be the identification of some structures in the brain, and then those features are being fed in a machine learning model, and we have an output if the patient had multiple sclerosis or not. In the deep learning case now, we omit the step of feature extraction. So the model identifies which of the areas, which of the features, attributes of the image are important in order to perform this classification test. Deep learning really brought a big evolution in the field. It has tremendous power when we have enough data. This is the first prerequisite for deep learning. In healthcare, this is not always the case. And a drawback of deep learning is, since we miss this feature extraction step, we are not always sure based on what feature or which area in this case, or what attribute of our data point the decision was made. And in healthcare, this is really important. We need to know why our model gave a specific answer. So we need to have explainable results. So keep this in mind for later on. If you start searching in the internet about applications of AI in healthcare, you will see thousands of articles, starting from biology and medicine and vaccines, to cancer detection, to rare diseases, to EEG and wearable data. So some of them that we will try to highlight in this webinar are the following. We have medical image analysis. We will see some biomedical signals and wearables. And we will also try to highlight the future of AI with some applications like digital twin and privacy-preserving machine learning. But let us see a general pipeline, let's say, of how implementation of AI in healthcare is being done. As a first step, we need to collect our data. Our data is the most important part of AI. We need large amount of data, especially when we want to employ deep learning and good quality data. So as we usually say in AI, rubbish in, rubbish out. So it's really important to have good data, but also good labels, especially when we have supervised models, as we usually do in healthcare, because we don't have lots of data that could result to unsupervised case. So we need our doctors to provide accurate labels that will help the model to perform the correct classification task. And there is always a direct link about the data that we have and the goal and the question we ask to AI. We cannot ask to AI things that would not provide knowledge for. And then in the last step, we have the data processing from the AI system that learns how to behave according to the labels, according to the directions we provided with the help of the doctor. So, can AI replace the experts? We see a lot of talk on the news and a lot of buzz around this. Is this a threat to the experts or not? Let us try to explain via some applications in healthcare the answer to this question. So, I will try to present two big families of applications. The first one is about wearables and AI, the doctor of the future, as we might call it. In generally, what is commonly being done now, you visit your doctor in different time points. So you can see in the first episode, you visit the doctor, and then there is a checkup a couple of months later. In between the two checkups, the health of the patient might fluctuate, and you can see the three different lines. Despite the fact that the health of the patient is different in the meantime, the doctor will probably see the same situation. So it is much better if we manage to have intermediate information for the health of the patient between the checks of the doctor. That's why we have different wearables that are being designed and will provide more data in between the visits to the doctor. We have EEG, wearable EEG in the ear or behind the ear. We have our wearable watches that provide ECG, respiration, and other information. We have our mobiles, etc., etc. All those wearables provide lots of data. Of course, it's time-consuming to the doctors to analyze this data, but as we said, a lot of data is good for AI. So AI can help in doctors in the analysis. And let us see 3 small use cases with wearables. The first use case is the epileptic seizure detection outside of the hospital. So when a doctor provides a treatment to the patient, he or she needs to see how the patient reacts to the treatment. So he or she needs to see the amount of seizures that the patient had in the home environment. So he needs an accurate diary of the seizures. As we see in the literature, most of the patients fail to accurately report the number of seizures that they had, especially in some types of seizures, like absent seizures. They do not know when they had a seizure. So there is a heavy under-report of seizure events in the diaries that are being kept by the patients or even the caregivers. So we need an automatic detection of the seizures while the patients are in their home environment, and AI can help on this. So for example, I have here a feature-based algorithm. I want to explain, give an example of what features mean. For example, in this case, we have from the knowledge of the doctors extract useful information in the time domain, like the zero crosses of the signal, the cross correlation between different windows, or also some frequency domain information. And we also post-process the labels of the signal. So for absent seizures, which is a type of seizure as mentioned, we achieved with this model a very high sensitivity of above 0.98 with low false alarms. So we can provide very accurate detection of the seizures that the patient had in his environment, much better than the patient himself, actually. But when the data gets worse in terms of data quality, or more noisy, or the type of seizures are more heterogeneous, then AI have problems. And I will give you a second example. So here you can see a model that was designed by our team in Q11 in 2020. This model is not feature-based. It is a neural network, multimodal neural network, actually. So it doesn't need features. It just takes the data. They are processed, pre-processed with different approaches, and then we have some fusion, and we get the classification task, the seizure detection. So this model participated in a huge seizure detection challenge with the biggest available seizure dataset. It was called Eureka Challenge, and actually it won the first place. So we won the competition by far. We are biometry irregulars. So we won a big challenge about seizure detection, but if you see the numbers, if you see the sensitivity, it's just 12.37. It's actually cannot be used in clinical routine. It's very, very low. But why do we see such a difference? I mean, from a model that reaches 98, when we move to a bigger data set, so theoretically more information, we lose our accuracy. The answer is on the type of the data, as I said before. We have much more difficult data set here. We have different types of seizures. We have really noisy cases. We have a low SNR. So the AI is still, in this case, not able to be used in a clinical route, even the best AI example, the best AI architecture. So although it can be used for specific cases, it cannot be used for all the cases and all the type of data. Similarly in the sleep monitoring. So usually the patients that have some sleep-related problems, they visit the hospital, they monitor their EEG and EOG while they sleep. You can see on the left side how a healthy patient would look like, and how a patient with REM behavioral disorder has his brain signals, EOG and EMG. You can see the difference between the two signals. So usually, based on the signals, we extract the hypnogram, and we can detect the stages, different stages of sleep. So AI, when we acquire the data in the sleep lab, so within the hospital, provides really good performance and achieve human-like performance. But if we move to home setting with wearable EEGs behind the ear, as you can see in this picture, the AI doesn't achieve to have similar performance like the clinicians, although it keeps the same statistics. So we must keep in mind, again, that when we have less accurate, less good data and not enough data, AI cannot do miracles. Okay, so in the third use case, we can see a machine learning application for patients with multiple sclerosis and Parkinson. Here we try to identify the freeze gate, and I'm using this example to show you that it's not always necessary to use the most complex models or the biggest models. In this use case, as you might see here in the sensitivity, the best performance is achieved with a support vector machine with a linear kernel. So not so complex model, let's say. And furthermore, if you see the next example, where we try to depict the number of features and the accuracy in the y-axis, you can see that with smart selection of features, we have a better performance with a lower number of features instead of a higher number of features. So more is not always better. It can be that some simple models or slightly less simple, let's say, models can provide better performance in some use cases. Let us move to one of the fields that AI and deep neural networks are really thriving. I mean, language models like ChatGPT and computer vision, medical imaging in healthcare, are the two fields, the two sectors that AI is really good, and deep neural networks are really good. So a dataset that has been recently released with a model from Meta, what is called Segment Anything, SAM. It has been trained with 11 million images using more than 1 billion masks. Some of the masks were created by AI and confirmed by human annotators. Some were already pre-existing. Tries to create a ChatGPT for images, let's say. So it is based, similar to ChatGPT, to a prompt decoder. So it has three parts: an image encoder, a mask decoder, and a prompt decoder. So the user can write in the prompt what he or she wants, and there are different ways to make the segmentation of the image, either defining a box around the area you want to search, or by defining some points, or by the text that I mentioned before, like segment me, the scissor in this case. So the performance of this neural network was quite tremendous, but in the healthcare domain, it didn't work perfectly, as you will see in the next example. So recently, some researchers provided an alternative solution where they kept the image decoder and the prompt decoder similarly, but they just optimized the mask decoder here for medical imaging applications. And as you can see, the performance is really good. If you see the ground truth and the MedSum, which is the modification of the segment anything algorithm of Meta, the segmentation of the different medical images is almost perfect. So AI really helps into segmenting very good these medical images. Of course, you must see that in this example that I'm showing here, they used the bounding box. So they identified with a box the area that they want to segment and search. In the fully automated version, where we don't have bounding box, the segmentation is not as perfect as in this case. But still, medical imaging and computer vision in general is a field that AI is doing really good. And there are different applications for this, like the kidney biopsy assistant tool. You can have a biopsy done automatically by a neural network, as you can see here in this use case. But let us move to something more futuristic, how AI will evolve in the next years in the healthcare. We have the applications of medical imaging, signal processing, and wearables that it's already being used in clinical routine. Of course, it will improve furthermore. But there are some fields that people predict that will be the future of AI in healthcare. And one of those is digital twins. I have here the definition of what a digital twin is from IBM. A digital twin is a virtual representation of an object, and is relevant for any field, manufacturing, cars, etc., etc. And it gets updated in real time with data when they arrive, and it uses different simulations to predict the response of this object, the digital version of a human, of a car, of everything, to specific decisions. So it means that in healthcare, you create a treatment and you can predict the response of this organ to the treatment. And as it is predicted by different industries, the digital twin sector will be really emerging the next years, and in combination with synthetic data that will be used to increment the data that we have for machine learning, it will be one of the sectors that will have the biggest evolution. But how this can be used in healthcare? I have here a use case, the cardiac digital twin. So we have the heart of a patient, and we want to create a digital twin of the heart in order to see and monitor the evolution of the health of the patient. So this tool could support patient risk stratification, could support continuous health monitoring, and as I mentioned before, identify insights about different treatments. So when you want to make, for example, a surgery or an ablation to the heart of the patient, you could first do it on the digital twin and see the response or optimize the treatment. As a use case, heart failure is commonly used, but of course can be scaled to other diseases, organs, or the entire human body in the future. And I have use case that was first done by Philips. Usually, what's the process that you follow? You get some anatomical images of the patient, so ultrasound in this case, or CT. You extract a mesh. A mesh is a 3D structure with finite elements that provides an image of the heart, as you can see in the first line here. Then you create such generic models from different patients. When a new patient comes in, you take a similar medical image and you try to adapt the model to the image of the patient. So you bring the model as close as it can be to the generic one. You optimize the model towards the image of the patient. Of course, this has a lot of drawbacks. So it is based mainly on medical images, as I mentioned. The model is not updated, and we said that digital twin is a model that continuously updates. So in this case, we don't have information from the everyday life of the patients, and we don't have enough data to build models for rare cases, so for patients that are not in the common cohorts. So what we are trying to do, and what many colleagues of ours are trying to do, is to extend the digital twins. So if we try to represent the span of biomedical data in this circle, we can separate them to dynamic data and static data. And currently, what we are using is only a part of the static data, the ultrasound and the MRI or the CT that I mentioned before. But we can extend our digital twins with much more data, like ECGs, genetic information, blood tests, the electronic health records of the patients that will provide much more information about the health of the patient, but also dynamic data that will update our digital twin in time, like wearable ECG, oximeter, etc., and also provide some extra types of data, not non-medical, demographic data, the family history of the patient, and the everyday activities, how the diet change, how the exercise change affects our heart. So if we have information about all those aspects, we will provide a better digital twin for the patient, and we can monitor better the condition of the heart of the patient. Of course, we can always amend our data set with synthetic data that will represent cases that are difficult to monitor, to cut. Usually, digital twins have been built with models that are based in some differential equations that define specific properties of the heart. So the hemodynamic function of the heart, the mechanical function of the heart. We have specific models like the Frick's law or other differential equations. And via continuous simulations for every patient, we try to find the optimal values of the differential equation. And based on this, we create the generic model. This means that we need a lot of time, computational power. We need to estimate millions of parameters in big and complex differential equations. And that is where AI can come in a concept called physics-driven AI. So we combine the knowledge from physics, the differential equations that I mentioned before, and we just try to optimize those equations with AI. So we do not create an AI model from the scratch, where we have the problems of interpretability, as I mentioned before, but we use as a starting point the differential equations we know that can accurately model the function of our hearts. So this provides clinical interpretability, contrary to a purely AI-based model. It doesn't need a significant amount of data because we have a starting point that is quite good, based on prior knowledge and differential equations. But after the initial training, it doesn't need to run all those simulations that the usual computational model needs. You can quickly find the optimized model of the digital twin with the use of AI. So this is a sector that I really believe that AI will play a significant role in the future. And the last family of applications that I will mention is privacy-preserving applications. As you probably know, the healthcare data really segmented in different silos. So we don't have a lot of data lying on the same computer, in the same database. We have usually our health data in hospitals. It can be in biopsy centers, etc., etc. And this is mainly due to privacy reasons. Medical data generally cannot be shared. We have GDPR in Europe. Also in China, USA, they start having some privacy acts. Very recently, the previous week, we had the AI Act in European Commission, where the applications of AI in healthcare are considered of high risk. So we have a growing concern of data privacy. So we cannot share data, AI needs data. So what's the solution? Federated learning and other privacy-preserving tools can be a solution to this. So instead of gathering our data in the same silo, we can create models that have access to the data remotely. So we create a model, we share some weights and information of the model to the different silos. Different silos update the model based on the data that they have, and they send back only the weights of the model. So let's say the centralized model never have access to the data, never gets private information from the data. So in this schema, for example, here you can see what I mentioned. We create a global model in our server. We share with the different hospitals some information about the model. Every hospital updates the model based on the data that they have, and they give back the weights. We have this iterative process. Our model is optimized, and each hospital gets the result of its own data based on a model trained in the data of all of the patients. So we can use much more data to train our model. So we can use AI tools, deep learning tools, but we never see the data. So we keep the privacy of health data secured. So coming back to my initial questions, can AI replace the expert? I think that the answer will always be no, but it can definitely assist them. There are multiple ways that AI can help to improve our healthcare and the treatment of the patients, and most importantly, the everyday life of our patients. As a conclusion, I want to mention that AI in healthcare has and will have a great impact in the next years, mainly in the automation of big tasks where the doctors do not have the time and the capability to do all those manual tasks. AI can really give them solutions, and we always need very good data. So we always need the help of our doctors to provide us prior knowledge, to provide labels on the training data, to improve AI and bring it into practice. And going into practice means much more than accuracy. So you must not see a model if it's good only based on some metrics like accuracy. Bringing AI to practice and into healthcare is a bigger conversation, and we need our doctors to achieve it. So closing this webinar, I would like also to advertise a MOOC, massive open online course that we are designing. So if you are interested for AI for healthcare and you want to get more information about how models are being built, which features are important, and see much more use cases and talks from doctors that they have been using AI, we will be glad to see you in our course that will be released on February the next year. So thank you very much for watching this webinar. I hope that I provide you some information about how healthcare will look like with AI the next years, and understand that we must not be afraid of AI. It's a tool that can help and improve our healthcare. Thank you very much.